If there's one thing programmers are all good at, it's having opinions on technology they've never used before. That's why if you tell your friends that you're a Vim programmer, they'll all tell you to get a grip and just use VS Code, even though you write software 10 times faster than their poor little monkey brains can handle. It's also why every other Reddit post is a flame war between object-oriented elitists and functional programming purists. As a quick reminder, object-oriented programming, or OOP, revolves around encapsulating your business logic and data together in classes, which can then act as templates for creating objects that share the same functionality. The 5 pillars of OOP are inheritance, polymorphism, encapsulation, abstraction, and self-hatred. The language most commonly associated with object-oriented programming is Java. In Java, everything must be a class, including your program itself. On the other hand, functional programming is predicated on extremely painful mathematics and often involves piping data from function to function, performing atomic operations on your data. A pure function will produce the exact same output if given the same input, and will produce no side effects. Popular functional programming languages include Clojure, Elixir, and Haskell. Okay, I hear you asking, but what about Python? Python is an interesting case. In Python, everything, even a function or class definition, is an object. Python shares a lot of the common features of object-oriented languages, allowing you to create classes and inherit from superclasses, but it also has functionality that you'd normally see in functional languages. Python allows you to define functions in the main body of the program, and functions are first-class citizens, meaning you can pass them into other functions. Python is extremely flexible. If you're coming from Java or C# and want to program everything in an OOP style, you'll be able to accomplish most of the things you want. If you're a previous Clojure developer, you won't have too much trouble replicating FP patterns in Python either. Much of the beauty of Python, however, is that it doesn't force you down one road or another. You can use features of both programming paradigms to create readable, extensible code that should keep your codebase maintainable, even as it grows. I've written a dumb program, and I'm going to show it to you 3 times. The first time will be in OOP, and the second in FP. If you haven't gouged your eyes out by the time you get to see the same thing a third time, I'm going to show you a beautiful Pythonic mixture of both. Along this treacherous journey, I'll highlight the strengths and weaknesses of each style, so you'll have something to work from when architecting your next Python project. And if you stick around to the end, I'll show you a real production use case for the combined OOP plus FP style. For the object-oriented version of the code, we're going to start by creating 2 classes. The first is an abstract logger class that defines a single method log that takes a string as input. We also define a named logger subclass that logs its name and message to the standard output. We've also created a basic animal class with dog and fish subclasses, which we'll use later. Here we can also clearly see one of the benefits of the OOP pattern. By defining fish as a subclass of animal, we've removed the need to define the speak method on the fish, though it'll still be able to speak. In small examples like this, it's not that important. But in a larger program, it could save us some headaches by only having the logic defined in one place. However, it also brings to light a problem. If we wanted more animals that could run, we'd probably create a running animal class between animal and dog that defines the run method, and potentially also a swimming animal class for the fish, which is where our hierarchies start to get more complicated. Moving on to the rest of the code, you can see that we've also created an app class to hold the main logic of the program. This follows the Java pattern, and contains only one method, the main method. We execute this main method to run our program, which creates a dog called Fido and a fish called Goldie. Each gets a named logger instance to output to stand it out with. We can now run the code, which produces the following output. So that was the object-oriented version of the code. But what about the functional version? From the get-go, we can see that our abstract logger class has simply become a type alias for a function that takes a string as an argument and returns nothing. We've also defined a named log function to deal with printing to standard out. A little further down, you'll see that instead of defining classes for our animals, we've instead defined functions that represent the actions the animals can perform. These take the name of an animal and a logging function as parameters, returning the same things. We do this so that we could compose these functions into pipelines later. The logic that used to be encapsulated in the app class has now just been moved into a main function. That way, we don't have to define a whole class just to get some words to print to a screen. The keen-eyed amongst you will have noticed that our named log function doesn't match the logger type alias we defined earlier. To get around this, we create a partial function application using functools. This takes a function as input and returns a new function with some of the parameters pre-filled. In this case, we pre-fill the name parameter to get something that adheres to the logger type. However, Since we're not encapsulating data in anything, it becomes difficult to add more attributes to our animals. We'd probably have to start using dictionaries and pass those around, but you could end up with a dictionary being created incorrectly and resulting in a key error later down the line. We also have the problem there's no way of validating that an animal passed into a function can actually perform that action. So we might end up with a barking fish. So we've established that both of the previous options are trash. So what do we do now? Well, we're going to bring in a few more Pythonic bits and pieces to pull away from the traditional OOP and FP paradigms, combine them a little, and hopefully make the code cleaner and easier to read. The first thing you'll see here is that we've kept the logger type and the named logger function. Since our logger only does one thing, we don't need to encapsulate it in a class, but it's useful to have a type alias so that we can substitute our named logger later down the line. If you're interested in cases where a logger might need to be a class, you can look at Python's built-in logging library and its handlers, or the struct-log library and its log processors. We've also moved away from traditional classes towards the more concise data classes. Python will create the data class constructors for us, so we don't need to write them ourselves anymore, and it's much easier to read and modify the class attributes if we want to. We do, however, have a post_init method, which is something added by data classes to allow you to run some initialization code after the object has been created. In this case, we're using it to instantiate a default logger if the user hasn't provided one. This makes our object initialization code much cleaner later. You'll also notice use of Python 3.11's new self type here, and the methods on the animal classes and subclasses all return self. This will allow us to chain the methods together nicely in a functional style. If you wanted to make your object immutable, you could make all these methods return copies of the object instead. Finally, the main function is again just a function. I will never understand why Java is the way Java is, and the phrase public static void main string args still gives me nightmares. Okay, so this example was extremely basic, I'll admit, but it served as a good starting point for this discussion. What I'll do now is go over how these concepts are used in production, specifically using two of my favorite Python libraries, FastAPI and Pydantic. FastAPI is a lightweight API framework for Python, and Pydantic is a data validation and settings management library. I'm not going to go into detail on either, but you'll see that these are both very well designed libraries that take a lot of what I've said into consideration. Pydantic allows you to define data structures using Python classes, and then validate incoming data and access it via object attributes. This way we can avoid problems that stem from working with dictionaries, and you'll always know that the data is in the format and type you expect. FastAPI builds on top of this, allowing you to define a HTTP API using Pydantic models as the inputs and outputs. In FastAPI, you also define your routes using Python decorators, which are another common feature of functional programming. This example is for an inventory management system. It defines an item, which can have an ID, a name, and some attributes, which are stored in an item attributes class. We've only got one attribute here because I'm lazy, but you get the general picture. I'm also using a dictionary as a mock database here, but you would use an actual database in production. I would recommend the SQL model package, as it maps nicely between Pydantic models and the SQL Alchemy ORM. I'm then using FastAPI to define a single route that allows you to search for an item by its ID. Notice that this just returns the item object itself. Under the hood, FastAPI will convert it to JSON, as you'll see in a minute. If we can't find an item with the ID specified, we raise an HTTP exception with a status code of 404, which FastAPI will return to the requester with the detail we provide. I've now got the app up and running using Uvicorn, a Python web server, and I can navigate to localhost port 8000/item/1 to get the item with ID 1, and you can see that we get a nice JSON response without having to deal with the serialization ourselves. If you look closely, you can also see that the item attributes object has been converted to JSON too, which would have been more difficult if we were trying to implement something like this from scratch. If we search for an item with ID 100, we get a 404. If we use a string for our ID, we'll get a 422 unprocessable entity error, because we defined our ID as being an integer. Obviously, this isn't the only way to combine programming paradigms such as OOP and FP, and there are lots of design patterns you can implement to make your code more simple and easier to read. Get subscribed so you don't miss future videos where I dive into those in a little more detail. While you're here though, why not check out the #1 thing you can do to speed up your backend code in this video here. Thanks for watching, and I'll see you next time.